you. I thank the organizers for this invitation, this very interesting conference. And as the variety of topics is quite large, I felt like I could actually give a non-purely combinatorial talk, so it will be mainly algebraic, but there's also underlying combinatorics. So my main subject is this Macdonald theory. The Macdonald theory is the theory of Macdonald polynomials, as we know it. So the original version is present these Macdonald polynomials as a family of multivariate orthogonal polynomial with respect to a certain measure, which has parameters, interesting parameters, a q and a t. And so that's how it was originally introduced by Macdonald. But then it turned out that this was just a sort of emerging part of a gigantic iceberg. And the name of the iceberg is DAHA, Double Affine Hecke Algebra. And so instead of showing you the polynomials first, I will show you the DAHA first, right? And so DAHA naturally leads to operators, and the Macdonald polynomials are presented in this way as common eigenfunctions of those operators. So it's a family of commuting operators, so of course it starts smelling like integrability, and there's all sorts of things you can deduce from that. And DAHA has very interesting properties, many automorphisms, and among them there's a duality. And this duality from the outside, viewed from the polynomials, is really a duality between, say, the eigenvalue equation for the polynomials and the Pierry equation for the polynomials. And I'll show you how this can be thought in a sort of more elegant and maybe a general way by use of what are called universal solutions. Okay, so there's a universal formulation of that duality. And then the rest of the talk is just to show you that, well, it's the same everywhere, essentially. So Koornwinder theory is the next interesting set of multivariate polynomials, the Koornwinder polynomials. It started with Askey-Wilson polynomials, which are just Koornwinder in one variable. But more generally, there's this Koornwinder theory, which has many more parameters, even than Macdonald theory, and which has a very interesting property that by specializing these parameters, you can actually recover all the Macdonald theories for classical Lie groups. Okay, so this is A type, and this contains as specializations via the types. Okay, and finally, recently, Arthamonov and Shakirov introduced a genus 2 version of Macdonald theory. So Macdonald theory, because of DAHA, as I will show you, has naturally genus 1. Okay, and so they managed to introduce a genus 2 version of that, which has its own restrictions. They introduced it coming from very far away, from refined Chern-Simons theory, but nevertheless, there is a consistent theory of Macdonald polynomials in genus 2, and I'll show you that this notion of duality that I'm introducing here also goes over to that case. Okay, so that's the plan. So let's start with the good old Macdonald theory in type A. So DAHA. Okay, so DAHA, this is the most boring slide of the whole talk. It's the relation of DAHA, right? So double affine Hecke algebra. So it starts with Hecke, the H. This is just the braid relations plus the condition that you have two eigenvalues. Then you have a bunch of operators X and Y, which you can think of as positions and momenta, which don't commute, of course. So they have relations with the braid generators and then relations among themselves. And this is actually the main relation, because all the others are kind of children of this relation. And I'll explain to you where this relation comes from. So it mixes up, you see, you want to commute x1 and y2, two neighbors in this list of parameters, of all operators. And then to commute, you need to insert a t1 squared in the middle. Okay? Another way to say it is that the group commutator of x1 and y2 is equal to t1 squared. That's another way. And then, so there's two parameters, q and t. So t is hidden here by square root, right? So these two eigenvalues are given in terms of t. And Q is a sort of global property that if you take the product of all the operators xi, so it goes up to the rank plus 1, and try to commute yj through them, you will recuperate a factor of Q inverse here or of Q here. So it's a property that has to do with winding around some loop. Okay, and so one of the main applications is torus not invariance, and of course all this has been developed and introduced by Cherednik. Okay, so Daha. So how I view Daha is like this. So you have pneumatics on your car, right? The air chamber, and and this is a solid torus, right? It's a torus but with a certain thickness. So you can represent that by a big piece of Marseille soap, right? With the left and right identify, and the front and back identify, and then the top is open to the air, and the bottom is the inside of my air chamber, okay? Now, generators of my algebra will connect the top to the bottom, okay? So the question is, how do I multiply generators? Well, I have to concatenate my pieces of soap, so I'm just putting one air chamber inside another, right? And I can therefore concatenate in the direction from the inside to the outside. Okay, so I call that a sort of matryoshka, because but it's kind of hard to realize because it's of genus 1, but anyway. Right, so it's genus 1 because you have these two cycles, A and B, right, due to these identifications. Okay, so the T's are the simplest operators, so they, like I said, they connect the outside to the inside, and they just braid the two points I and I plus 1, right? So you set points 1 up to rank plus 1, 1 up to rank plus 1, and R plus 1, so that's AR, right? So the rank is actually R plus 1. Huh? Okay, and so you have T inverse, according to how you cross, above or below, right? And then the braid relations are just obtained by pulling the strings, right? So you put 3 of my soaps on top of one another, one with I plus 1, one with I, you pull the strings, and you rearrange the strings, and you get the braid relation. Okay? The Y's are more interesting. So this is the B cycle direction, right? So now what you do is you send I to I, but to do that you go around the torus along the B cycle, okay? And then Y inverse is the same, but you go the other way, right? Instead of starting to the left, you start to the right. Okay, so these are the two operators. And of course for X, it's the same thing, but now you pass through the A cycle, so it's front and back, right? Okay, and then there's another generator which is a bit harder to write, which is the cyclic permutation of the points, but you can actually obtain it just using X, Y's, and T's. Okay, so here the relation of commutation, or like I said, of group commutator, it's easier to view it this way, right, between x1 and y2. So I drew for you x1 and y2, and then x1 inverse and y2 inverse, according to the rules I gave you before, right? And now you have to remember that I have identification of the right and of the left, right, along the B cycle. And so, well, you have to just work hard enough, realize that this connection which is inside my blocks is the same as if I had put it here, because these points are identified to these points. And so this guy, which is numbered 1 here, connects actually to the number 1 below, and this guy number 2 here actually connects to a number 2 below. So you pull the strings, and you end up with this guy, which is T1 squared. Okay? So a nice way of understanding the relations of Daha. Okay, so now I go down one step and to the actual Macdonald.
Sorry,
yes?
Can one say that it's some kind of like fundamental group of conversion space of points on a torus?
Yes,
okay.
Yes, absolutely, yeah. So it's just a very nice visual illustration of the relations that were a bit dry, I must say. Okay, so now we're considering the spherical Daha. So in spherical, there's just the idea that things are going to be symmetric. And so instead of taking all the generators X and Y and T, we're only considering symmetric generators in X and symmetric generators in Y. And so there is a functional representation that you can, which is completely explicit, in which you can write what these operators are, acting on functions of n variables. So here n is r+1. Huh? And is the rank. And so the xi are going to just act like multiplication by a number, right? But the yi are going to act as difference operators, right? And so they are a symmetric combination. So EA is just the eighth elementary symmetric function, is going to be a nice operator like this, where this is a rational fraction of the x's. But here you have these operators gamma indexed by some A element index inside one n, and the gamma of a set is just the product of the gamma's elements of this set, and gamma I just shifts the xi variable by a multiplicative factor q. Okay, so this is a difference operator in the sense that instead of taking differentials, you just multiply variables by some parameter q.
So actually the sum is not over small I into capital I, but it's over just over sets of size A.
Yeah, you're right. You're right. So thank you. Yeah. This thing here should be here, and it is here. And here there's missing that I has to be a subset of 1n. Thank you. So what you can prove is that these DAs commute among themselves, and these are the famous type an-1 Macdonald operators. And so, like I said, their common eigenfunctions are monic. So you can normalize the eigenfunctions so that they are monic.
But what about DA? Because it is
DA is is this guy.
it's all right.
Yeah. Sorry. DA is defined as this element of there's a row if you want. It's the representation of this element in the functional representation. Sorry. I try to write as little as possible, but then things are missing, sorry. So the P lambda, the common eigenfunctions, I normalize them so that they are monic, and they are monic polynomials indexed by partitions of some integer n. And these are the eigenvalues. They are elementary symmetric functions of the variables s, and s is just built out of lambda. So here you will recognize rho I, right? I forgot the name in the Lie algebra. It's a standard vector in the Lie algebra of an-1, and it's just the half sum of positive roots, for instance. So okay, so the notation is S like this, but it stands for actually the collection of SI given by these formulas. Okay, and the rank here you can see as just the maximum on the length of the partition. Okay, so a very important property which was first devised by Macdonald in the A type and then generalized by Cherednik is the following. It's that actually these polynomials, lambda is like the degree, right? And x is the variable inside. So there is a way of interverting the two, right? So you interchange the degree in the variable. Okay, so to do this, of course, you have to specialize your variable to something that involves something which is similar to the degree. So it's this parameterization. And then this quantity, properly normalized in this way, is symmetric in lambda mu. Okay. So this was immediately proved for type A, but essentially Daha was extremely useful for proving it in the other types. Okay. So I just want to show you now how this duality relation allows to immediately generate Pierre rules for these Macdonald polynomials. So Pierre rule is just what effect does it have to multiply the polynomial by an elementary symmetric function of the variables, right? So it shifts actually the lambda variable now, right? So the dA was shifting x, but now the EA is shifting lambda. So there's a difference operator. I call it of S because we know that S is another way of coding lambda, right? And you can get it from the duality. So let's start from the eigenvalue equation, right here. dp is ep, right? Then I just write this guy by doing the specialization x is 0 q mu, right? And I used my previous slides relation, which is right here, to transfer the mu from the inside to the outside, right? So I do that. So now I have p mu's, okay, with the correct normalization. And I remultiply by this denominator, right? And I find that a certain conjugation of dA by this denominator actually acts on p mu in the same way as it did on p lambda, multiplying it by EA of S. But now, the great thing is that S and X are just abstract variables, and I can interchange them. Okay, so if I just rename XS and SX, I get this equation here. So the dA of S now, which is a difference operator in the S variable, conjugated by the correct object, is going to be exactly the generator of the Pierre rules, as you can see, okay, for P mu. So duality implies Pierre rules. Okay, so explicitly this is what so I call it H because I think of it as a Hamiltonian, right, a Macdonald Hamiltonian if you want. It's, of course, these guys commute with each other, just because the dA commuted with each other, right? And they generate the multiplication by EA of X on the polynomials. Okay, so same notations as before, but now you see everything is in variable S, and Ti is now the shift of the S variables. So same thing as before, change of names. Now, same thing, not quite, because this formula is not quite the same as the one we had for the Macdonald operators. And the whole thing in between is quite simple. It's just the conjugation with respect to this sort of norm of P mu. Okay? All right. So let's reformulate this in a sort of more abstract and elegant way. So let's say that instead of looking for monic polynomial solutions, we just look for solutions which start with x to the lambda and then have a series expansion, right? But lambda now, not necessarily an integer partition, just some sort of arbitrary number. And the really nice thing is that this same equation here, if I expand f as a series of negative roots, right? So this is the positive root cone, but now I have minus beta, so it's negative roots with coefficients, then this equation becomes triangular system for the coefficients. So you can determine them all, okay? And this is true because if you look at dA of X, you can always write it, express it in terms of negative roots also. So you get some nice, well, I'll give you some example to see what goes on, but, and so it's, this series is unique, of course, the solution C beta is unique because you get a triangular system up to the normalization, but the normalization is that this thing starts with 1 because we want to mimic the monicity property. Okay, so here is the example of SL2. So D is just a sum of two terms, right? So shift of x1, shift of x2 by Q. So this is what it does to a function f of x1, x2, right? And the denominator that I had in the coefficients here, I put on the right side. And I express everybody in terms of this ratio x2 over x1, which is the negative root, right? It's x to the minus alpha 1. Okay? And so you see here, well, that's it, right? You stick in there a generating series with coefficients Cn of S1, S2, and this equation turns into a recursion relation for Cn, which is super simple, right? It's this equals this, and you can solve explicitly. So you have a coefficient Cm of this series, okay? So what good does it do me? Well, several things, right? So, but let's first just read the general case because it's the same story, right? So in the general case, I said this is rational. So same thing, I write f as a series expansion, but now on the positive roots, right, which are all these guys, and negative roots, in fact, yeah. And then the recursion relation for C beta, once I put all the coefficients in there, is just expressed in terms of shifts, right? So beta is expressed in terms of beta minus certain shifts, right? And so once you have a recursion relation like this, you can re-express the solution as a sum over paths. Okay? So you have a complicated sum over paths with products of weights picked up along the path, which gives you the coefficient. So it's a sort of a discrete functional integral expression for the coefficients of this Macdonald series. But what good does it do me, and now it's the point, is that this series actually contains the information on all the Macdonald polynomials. So this is a great thing. With one series, I get all the polynomials. And why? It's because this series actually specializes to Macdonald polynomials if I specialize this variable s to q to the lambda at 0, where lambda now is an integer partition. Okay? Before it didn't have to, but if I specialize, then the whole thing truncates, in fact, instead of being a series, truncates, and it becomes a polynomial. So the example of SL2, previous example, right, we had this. Now you look at this factor. If S2 over S1, which is given by these parameters in terms of lambda 1 and lambda 2, my two-row tableau, if lambda 1 is larger or equal to lambda 2 integer, then you will see that, of course, there's a cutoff here. When m is larger than n, than this difference, the coefficient is 0. So you get an effective truncation of a series, and that's a polynomial, and that's our Macdonald polynomial. Okay, so once you have said that, you can do the same with the Pierre equation, and write the universal solution of the Pierre equation, right? So by the same token, right, I solve this equation, and I can normalize it by C0 tilde is 1, and I also have a path solution for this guy, okay? So the first theorem is that the two series are related. Okay, we could expect that there was a function of x in between because h only acts on the s variable, right? But you can prove that they are proportional, and the proportionality factor is actually an infinite product, a sort of quantum d-logarithm, or quantum exponential, which involves explicitly q and q over t, right? And you recognize here the positive roots again, playing a very special role. And now the duality, you can repackage it completely as just a symmetry of a function phi, or a symmetry involving f, which is up to delta because f is delta phi. So these two are completely equivalent. Okay, so that's the duality for you. And of course, the duality, I claim, will reduce to the duality of polynomials. And when you write that, it means that there's a relation between the norms of those polynomials, the guys in the denominators, right? And this delta, this infinite product. But this guy is actually a finite product, and this ratio of deltas, when lambda is integer, is also a finite product. It's a ratio of two infinite products, but with many cancellations. Okay? So you can rewrite the Hamiltonian as just the conjugation of the Macdonald operator by this infinite product delta. All right. So there's a very interesting way now of rewriting the operator dA as just the conjugation now instead of delta inverse, because you have to go back somehow, of the product of shifts operators here, and then symmetrizing over x1 and xn, up to xn. So it's a very nice and compact expression for the Macdonald operators. And you can see that with this, the HA always will start with T1 TA plus other terms with coefficients. And that just means that you multiply by an elementary symmetric function. So you raise the degree by exactly what you need here. A T is basically shifting a lambda by 1, right? So it shifts all the lambdas in the polynomial by 1 that are hit by the elementary symmetric function. So it makes perfect sense. Okay, so now I can accelerate because you've seen all the elements. Koornwinder theory is just another of those theories. So there's a formulation in terms of Daha, but I don't have time to explain it. But let's say it's still of genus 1, just like the previous one. But it has essentially boundary terms. And these boundary terms correspond to these parameters A, B, C, D, right? So there's 4 more parameters than Q and T. And the fundamental operator, so the first order difference operator that will define entirely all the polynomials, is this expression here. So again, a shift, but now you notice that I'm summing also over a sign, plus or minus. And the reason is that now, instead of looking at polynomials of A type, we're going to look at polynomials of B type. And B type, we have a while group which also inverts the variable, not just permutes it, right? So symmetric with respect to this B type while group will be that my polynomials now are going to be Laurent polynomials because I can invert the variables, and symmetric Laurent polynomials. So that's why I have this epsilon. And here is where the parameters A, B, C, D appear, right? Okay, it's kind of technical, but you have Q, T, and A, B, C, D hidden in this formula. Okay, and this constant kappa 0 is also determined in terms of all the parameters. Okay, so the polynomials are eigenfunctions, and this shift with a constant, etc., were ad hoc so that the eigenvalues are this E1 hat of S, and E1 hat is just the elementary symmetric while symmetric function, so it's sum of xi plus sum of xi inverse. All right, here the S is still defined as tiro q lambda, but now there's a little parameter that depends on A, B, C, D. Rank 1 is Askey-Wilson, and the major application, as I mentioned, is that it specializes this to Macdonald theories. So here is the table. So this is the label of a Macdonald theory, right? So we already did A n minus 1, 1, so now we have B, C, D, and also for the same price, we get the twisted guys. And these are the values of A, B, C, D that you have to choose to get those theories. Okay? So this is just refers to Macdonald's notation in pairs of root systems. And this is this parameter sigma, which multiplies in the definition of S. So it's either 1, T1 half, or T. Okay. Duality. So there's a transformation which leaves Q and T invariant, but changes A, B, C, D, okay, like this, which is such that the same property as the one I described for A type is still true, right? So the polynomial lambda of X specialized at some dual expression involving another partition mu is symmetric under interchange of mu and lambda, except that you also have to switch to the dual parameters here. Okay, so it's a little bit more complicated, but essentially it's the same story. Okay, so of course the same story holds that you can get Pierry rules for Koornwinder very easily from this duality. Okay, and it's just conjugation of a Macdonald operator of the dual theory. So the Hamiltonian of a theory is obtained from the Macdonald operator of a dual theory. So in my table, so here is the dual, right? So you can see that everybody is self-dual except B and C. So it feels exactly like Langlands duality, right? So B and C are interchanged. Okay, so that's it. And of course, the next step is to do the universal solution, right? Just like we did for A-type Macdonald. You can repeat the exact same story, and you have the exact same specialization of this infinite series to Koornwinder polynomials. Now, the interesting thing is that if you do your specializations, like I said to do, you will realize that there's more information contained in this specialization, in this series, because it also allows to specialize to values of lambda that are not necessarily partitions, but G-type partitions. So for instance, for type D, the last part of the partition can be positive or negative, right? And these specializations are exactly obtained in my series. And so for B, it's even more striking. You have half-integer lambdas appearing, and with the specialization I said, it works too. So the duality, well, same thing. Same thing. You can prove that the elementary solution for Pierry rules is proportional to the elementary solution for the Koornwinder eigenvalue equation via an infinite product delta, which is slightly more complicated, okay, which involves all the parameters A, B, C, D, E, and also if you look at this ratio, these are actually the roots of type B, right? And then there's a square, so there's B and C mixed up, right? Sometimes it's called BC, by the way, this Koornwinder thing. And the duality is just that phi is, if you interchange S and X, is the dual, and F has the, accordingly, the relation coming from the top. Norms of polynomials, same story, okay? So you have a relation directly between the norms and polynomials and the ratios of these infinite products, and you have an expression, explicit expression for the Pierre rules in terms of the Macdonald operators and this infinite product. Okay, so now I come to how many minutes do I have?
Still have 9 minutes.
Oh yeah, plenty enough. So genus 2. Okay, so this is a long story, so I'll try to make it short. So Arthamonov and Shakirov in 2019 introduced a Macdonald theory for genus 2. So they came from very far away, that is from refined chain-Simon's theory on a genus 2 surface, which led them naturally to compute 6J symbols. And these 6J symbols they used to define Pierre rules. Okay, and so the compatibility between these Pierre rules finally led them to introduction of a family of polynomials, which they called genus 2 Macdonald polynomials. And after that, they figured the rest of the story, which is the Daha story, right? Which was hiding behind. So you have to, of course, have the right cycles on your genus 2 surface and repeat basically the story I was explaining. And you get 3 sets of variables x, 3 sets of variables y, one for each type of cycle. And so it leads naturally to 3 Macdonald operators that commute and the Macdonald polynomials finally. Okay, now the bemol which I have to apply here is that it's only in rank 1. There's some sort of no-go theorem which tells you that it cannot work in higher rank, at least not this story. Okay. All right, so here is what the operator looks like. So now my while group is something like Z2 times Z2 times Z2. Okay, so it's those signs I'm summing over, and then there's a third sign which is hidden here. And as you notice, my operators are now of second order in a sense because they are product of gammas, not just a single gamma. Okay, and they act on functions of 3 variables, x1, x2, x3. So these ij, etc., they live between 1 and 3. Theorem is the commutation of those operators. Common eigenfunctions are labeled by genus 2 partitions, which I have to explain on the next slide. So here starts the way we reformulated it with Rinat. We found a convenient set of roots, which are not roots because they are not roots of any algebra, but they play the same role, okay, in C3, so alpha 1, alpha 2, alpha 3, given here. And then a root system, so I also introduced this half sum of positive roots, right, which is 1, 1, 1. And the positive roots are given by just alpha 1, alpha 2, alpha 3, their pairwise product and their pairwise sums and triple sum, right? So there's a nice way of thinking of this lattice in 3 dimensions. I mean lattice, this set of roots. So if you so these would be alpha 1, alpha 2, alpha 3, and so these guys have x plus y plus z equal 1, right, in terms of their coordinates. Then the black ones have x plus y plus z equal 2, and finally the center has x plus y plus z equals 3. So I'm sitting in the plane which is perpendicular to 1, 1, 1. Okay, and so you see these are the 3. So it looks very much like the root lattice of SL3, but it's just an error of interpretation because it's in different planes. Okay, so this is my positive roots, and there's a positive cone associated to it. And now the genus 2 partitions are just the triples of integers, such that these dot products with the alphas, right, are even positive integers. Okay, and the while group, like I said, just corresponds to inverting independently the three variables. Okay, so having said that, I can rewrite my eigenfunction equation like this. So the eigenvalue is given in terms of a index k, such that alpha I plus alpha j is 2 epsilon k. Okay, so alpha 1 plus alpha 2 is here, and it's 2, 0, 0, so it's 2 epsilon 1, etc. So you have a nice way of labeling the eigenvalues by just one integer, whereas the operators are labeled by 2 integers. And it's not the complement in 1, 2, 3. It's more tricky.
You have 5 minutes.
Yes, almost done. Don't worry. So this is the natural way of indexing, I mean, of naming the variables, right? So I have xi, x1, x2 for each of those three guys, but I have sk here given in terms of sum alpha I plus alpha j, which is just 2 epsilon k, so it's just lambda k here. It's just to write something complicated, whereas it's simple. Okay, and so genus 2 partition, I gave a definition before. And so now the p lambdas, we can decide they're monic. And so we know exactly what the leading term should look like, right, with this condition of positivity. And that's the leading term. And then there's an expansion in negative roots, again, with my definition of roots. Okay, and it's finite, of course, because it's a polynomial. Duality. So the duality here is very simple. It just looks like this. And it gives you the Pierre rules, and then what we did is check that this duality led to the correct Pierre rules that these people had introduced. Okay, so you can play the same game of the universal solutions. Okay, so look for series expansion. So we know exactly, so this x to the lambda means just the leading term, like I defined it in terms of genus 2 partitions. Okay, you do it for Macdonald eigenvalue, you do it for Pierre rules, and you can solve, you find these coefficients by path model, just like before. Okay, and the path model involves shifts by positive roots again. So this root lattice is very important in this story. Okay, and so the specialization also recovers the genus 2 Macdonald polynomials, so everything works, and the duality, finally, is just the proportionality of eigenvalue solution and Pierre solution by an infinite product, which involves explicitly the entire set of positive roots, just like it did before, and then Q and T. All right, and the duality is just, everything is the same as before. So I think we have sort of a completely uniform way of looking at all these guys by just specifying the root lattice, essentially, or the positive roots, and this function. Okay, so you have the same story for the norms of the polynomials, and the Pierre operators are, again, given in terms of these conjugations. So just to make things more concrete, I wrote for you the Pierre rule operator, right? So, and for 1, and it's explicitly given in terms of these shift operators. So you see there's 4 terms because there's power +1 or -1 for each of these two guys. And the coefficients, you will notice, are all expressed in terms of these positive roots. Okay? So a very algebraic object we have here. Okay, so that's the end. There's many actually applications to this, but the main one is the connection to cluster algebras that Rinat is going to discuss in her talk, and in particular the fact that from Koornwinder theory you can get all these Macdonald theories almost for free. Okay, not completely for free, but almost. And the connection to cluster algebra appears when you take what's called the Q-Whittaker limit. So it's when t goes to infinity. Of course, my specializations involve t. So sending t to infinity is not uniform on Koornwinder, right? It's each object is special. Each case is special. There's another type of duality that I haven't discussed here, which people like Shirashi call point carré duality, because it's in relation with geometric interpretations, which we have also discovered in the genus 2 case. And there are other interesting questions, like the action of a mapping class roof, definition of a Fourier transform using these universal solutions, and still to do the combinatorics of these genus 2 Macdonald polynomials. Thank you for your attention.
Thank you very much. So now there's a time for questions, comments.
Why is genus 2 and rank 1? So what makes
it's apparently, I didn't understand the deep reason why, but apparently when they consider this refined Chern-Simons theory in genus 2, the thing collapses for higher ranks. They were not able to. I agree with you. I'm actually trying very hard to generalize this to higher rank because I can't believe it's not working. But actually, it seems to be extremely hard. So there might be something behind this. But I feel like I don't understand why. Okay. Now, higher genus, good question. I don't know. Probably it's just too difficult. I don't know. But I think these are good questions, yes.
Okay, Marek.
So thank you for beautiful explanation. And I have a question because I am coming from harmonic analysis and probability.
Which I avoid completely, as you notice.
So
yeah?
Is, and in my talk, when I'm speaking at type B, we obtain positivity because our orthogonal polynomial, which appears in that business, I don't know how this is related, are so-called Hermite polynomial for the classical case, but for the big case is with two parameters also. I don't know if
maybe it's a specialization of Koornwinder.
Yeah, maybe.
Okay. Yeah.
But my question is, if this is, there should be some positivity in your approach somewhere. So I asked you before.
No, I said that I avoided talking about orthogonality properties and things like that, but there's also a way of defining things with orthogonality conditions. So that's what Macdonald did first, and absolutely there is some measure which is really ugly. But,
this is not really my question. This is question of the Sergei Kirov. When we met in Paris, by the way, 2000. Was in other institute, Poincaré was Bian and Wojkulewski organized school, and he asked that question. Many people care. Unfortunately, he has passed away, but he and his famous habilitation book thesis, the asymptotic representation of. Is plenty of such a question. I know about positivity. The question was solved, but only in the case A n. So for other cases,
well, limit shapes and things like this. I don't know if any of those techniques allow to say anything about that. It's kind of a different.
I should ask completely different. But anyway, we should discuss maybe later. Okay. Thank you, and more beautiful.
Another question or comment. If not, we think that. Oh, Andrea.
I hope this is a tiny one. Those delta factors that you have, are they somehow one of those partition functions that you get in these semi-infinite strips, like in those Borolin model, the Magnon sectors, so that you can interpret your duality relation f equal delta phi delta inverse as a Tallinn model, one of those integrable Tallinn models that is.
Okay, so these products are all quantum exponentials, right? Or quantum D-logarithms, right? Which actually appear also in cluster algebra, quantum cluster algebra all over the place. So indeed, there is a way of expanding them as series, right? So the simplest case is just a single product, right? Infinite product. You expand it in series and you can interpret it in terms of I think fermionic segments on a line or something like this with a specific weight depending on the position. Okay, so there's certainly an interpretation. Yeah. of all these products. So yes, but now that it be exactly what you say, I don't know.
In flower also.
Yeah.
Okay, so I think we can thank the speaker and the participants of discussion.